Section 5.5, indirect proof and inequalities in one triangle. So we're starting with indirect proof, okay? Up until this point, we've been using direct reasoning. I mean, we have a given set of information, we have a proof statement, we're going to go directly using that information to get to our proof statement. In an indirect proof, you take a little bit of a different path. You start by assuming that the conclusion that you're given is false. Okay? So the conclusion is false. You then take that information and you run with it. You start saying what you can and building an argument, and eventually what can happen is that assumption leads to a contradiction. The contradiction has to be a violation of something we know to be true, a postulate, a definition, a property, a theorem. So essentially, by assuming the opposite of what someone says, you indirectly show that they're correct. Because by assuming the opposite, you prove yourself to be wrong. So that's why it's indirect. You are taking a roundabout way to show that something is true. And this can be useful in certain situations, okay? Write an indirect proof that a triangle cannot have two right angles. So think about that. Think about a triangle that has two right angles. Well, there's a right angle. And here's a right angle. And how do you make that into a triangle? Okay? Doesn't really work. So let's show you how to do that as a proof. First, you want to assume the opposite of the conclusion. So, we'll start off with a negation. The negation is that a triangle can have two right angles. So just the opposite. They say that it cannot, we'll say it can. Okay? Now that becomes a given. We assume that to be true. So when we go to look at our proof and we write out our givens, we have to include that. Right triangle ABC with right angles A and B. So we're saying we have a right triangle, and then two of the angles in there are right. So now let's run with that. Okay? Start thinking about what can you say about triangles? What can you say about right angles? Okay? If someone asks you, hey, what can you tell me about the angles in a triangle? Well, something that we know is that the measure of angle A, the measure of angle B, the measure of angle C equals 180 degrees. Triangle sum theorem. We know that about triangles. Well, what do we know about right angles? Well, if both the measure of angle A and the measure of angle B are equal, well, they're both right, so they're equal. They're both 90 degrees. That's the definition of a right angle. So just kind of using kind of this tertiary knowledge that we know. Yeah, triangles, the angles add up to 180. Yeah, right angles, they equal 90 degrees. What's the big deal? Well, start putting this information together. Well, the measure of angle A is 90 degrees. Let's substitute that 90 in. The measure of angle B is 90 degrees. Let's start substituting that information in. We don't know anything about the measure of angle C yet. But based upon the equation we have, what's going to happen to the measure of angle C? Well, we have these two 90s. Let's get rid of them. Let's subtract them from both sides. And angle C ends up not existing. It's 0 degrees. Well, if a triangle needs 3 angles, you need 3 measures. But if 2 of them are right, that doesn't leave any degrees left for the third one. So like in this drawing over here, yeah, here's angle A, here's angle B, but where's angle C? All right, so the drawing can kind of help guide your thinking, but here's the proof. So we did subtraction, which led to a contradiction. All right, a contradiction of something we know to be true about the triangle sum theorem and the measures of angles. So this contradiction leads us to a conclusion. These 3 dots, that is notation for therefore. So in conclusion. Therefore, a triangle cannot have 2 right angles. And we have our indirect proof. Take what they're telling you, assume the opposite, and then go with it. Eventually, you'll run headlong into a brick wall of contradiction. Example 2. Go ahead and take a look at that following this format. Check what you have with my completed notes online. So that's the first part of this section, is the indirect proof. The other part of this section, well, I got to remember how to get to the page. So the other part of this section, where is it? Aha, there it is. So angle-side relationships in triangles. So looking at the angles and the sides and how they relate to each other. Now I spoke in a previous video about how the larger the side of a triangle, the larger the opposite angle. So now let's compare multiple sides or multiple angles. If AB is larger than BC in a triangle, that means the angle opposite the larger side is bigger than the angle opposite the smaller side. So the red side is bigger than the blue side. That means the red angle is bigger than the blue angle. And then it can go the other way. If you look at the angles, so measure of angle Z is greater than the measure of angle Y. The red angle is greater than the blue angle. That means the red side is greater than the blue side. And what this leads to is a triangle inequality theorem, okay? And it says that in order for sides in a triangle to work, okay, you need some type of relationship between the 2 smallest sides and the largest side. For example, let's say I had a side that was 20, and then I had a side that was 3, and a side that was 4. There is no way to create that triangle. The 3 and the 4 can never reach each other. They eventually have to be extended far enough so that they reach. What this says is that the sum of any 2 side lengths of a triangle must be greater than the third side. But what it really breaks down to is just the 2 smallest sides must add to more than the third. Because, of course, the largest side plus another side is going to be more than the remaining. So you just have to focus on the 2 smallest. And they have to be more, because if you have a side that's 10, then a side that's 5, and a side that's 5, the only way these are going to reach each other is if they lie flat down on that 10. So one of them has to be just a little bit bigger, okay? So if we look here, we have the 2 shortest sides, 8 and 13. So 8 plus 13, is that greater than 21? We add those up. And 21 is not greater than 21. So 8, 13, and 21 cannot form the sides of a triangle. One of these two, the 8 or the 13, needs to be a little bigger. Down in example B, 9, 5, and 12. So if you take 9 and 5 and add them, will they be greater than 12? Well, you add 9 and 5, you get 14. So yes, that will work. So look at the remaining examples. Check my completed notes online.